We live on a piece of the Earth's crust which has had an immensely long and eventful history, at times shrouded in mystery. Here we tell how it has travelled the globe and more than once lain at the bottom of the ocean. How it was buried to red-hot depths and sundered apart. And how it was frozen under ice sheets before emerging, with some help from our ancestors, as the unique landscape of Britain. That, in a nutshell, is the purpose of this programme. It's a quotation from this booklet prepared to accompany the Geological Museum's exhibit, Britain Before Man. So we've come to the museum to highlight some of the major themes in the geological history of the British Isles by looking at the exhibits here and looking back over field visits we've made in earlier programmes in this course and in the foundation course. This is a reconstruction of Britain under ice, but not of the last, or rather present, ice age, but one that occurred about 650 million years ago in late Precambrian times. So Britain's experienced extremes of climate, and to remind you of some of the evidence for this, let's go back to the Science Foundation course and a visit we made to an open-cast site in Durham. The most obvious indicator of ancient glacial conditions is the occurrence of tillites. But here the tills, or boulder clay, we found were formed in the most recent Pleistocene glaciation. So this material is called boulder clay, and much of Britain is mantled with it, especially around mountainous regions and in areas of eastern lowland Britain, such as County Durham, where we are now. Well, if we could find fossil equivalents of this boulder clay, hundreds of millions of years old, with boulders floating in clay, then they'd give us some indication of the kind of climate that might have been in existence at that time, whether the area was glaciated or not. Well, in Scotland, we do find such rocks. They're about 700 million years old, and they look remarkably similar to the boulder clay we've just been looking at, except that what was once originally clay has now been forged into hard rock by heat and pressure. So this is evidence that Britain experienced a cold ice age type of climate 700 million years ago. But there have been times when Britain has had a much hotter climate. I'm standing on a coal seam that's about 300 million years old. So that junction between the boulder clay and the coal seam represents a huge time gap. And of course the coal seams are the fossilised remains of vegetation that grew in hot, swampy conditions like those we saw in Okefenokee. So 300 million years ago, in Carboniferous times, Britain experienced an equatorial climate. At the present time, equatorial rainforest areas are flanked to the north and south by hot, dry regions, and in parts of these occur vast sand deserts. Again, in County Durham, we visited a quarry in Permian sandstones lying above the coal measures, which exhibited fine dune cross bedding. Such indicators of desert conditions are found in many other Permian sandstones in Britain. These so-called new red sandstones are on the Isle of Arran. So about 250 million years ago, in Permian times, Britain had a hot desert climate. Clearly, the paleoclimatic evidence shows that over the last 700 million years, Britain has changed its position relative to the equator, and the paleomagnetic polar wandering curve for Europe confirms this. Going back through time, we can see that the paleomagnetic pole positions indicate a more southerly position for Britain than today. 250 million years ago, in Permian times, it lay in a latitude comparable to the Sahara today. An equatorial position in the Carboniferous, and before that, progressively nearer to the South Pole. But polar wandering curves can tell us more. Remember what happens when we bring together the polar wandering curve for Europe and that for North America by closing the Atlantic Ocean. The divergence since 200 million years ago indicates the opening of the Atlantic. And the match from the beginning of the Devonian, 390 million years ago, to 200 million years ago, towards the end of the Triassic, shows that during this period, the two continents were united. But the divergence before 390 million years ago suggests the two continents were separated by an ocean, the Proto-Atlantic Ocean, or Iapetus. Furthermore, fossil evidence indicates that 500 million years ago, the north and south of Britain lay on opposite sides of the Iapetus Ocean. British trilobites of this age fall into two groups. The group represented on the right is only found in northern Scotland, and that on the left only in southern Britain. The Iapetus Ocean was a barrier preventing these shallow water organisms migrating between the two areas. About 500 million years ago, this ocean was shrinking. The two continents moved together and eventually collided about 400 million years ago, producing the Caledonian orogenic belt that stretches from Greenland and Scandinavia into West Africa and Eastern America. As the Caledonian orogeny was a major event in British geological history, let's look in a bit more detail at how it developed. Some 700 million years ago, at the end of Precambrian times, there was continuous continental crust between areas which today are North America, to the left, and Europe, to the right. We know very little about the detailed paleogeography at this time, but as you know, the area lay close enough to the South Pole to be affected by glaciation. Around 650 million years ago, the continental crust was separated as the Iapetus Ocean opened. We don't know how wide this ocean was, so the division in the middle may represent hundreds of kilometres on either side of an ocean ridge system. At this stage, thick sediments began to accumulate on the Scottish margin of the new ocean. About 50 million years later, a relatively short period of subduction on the southern margin of the ocean is indicated by the occurrence of andesitic volcanic rocks and granitic intrusives in what is now the Midlands and Wales. But by the beginning of the Cambrian, it appears that both margins of the Iapetus were passive again, for there's no evidence of subduction-related igneous activity of this age. But by early Ordovician times, the Iapetus Ocean had begun to close, and as the closing continued, the sediments that had accumulated on the Scottish margin were folded and metamorphosed. On the other margin, volcanoes formed in the Welsh area. By late Ordovician times, the Scottish crust had thickened considerably, leading to increased metamorphism and the formation of granite plutons. At this stage in the closing of the Iapetus, an accretionary prism formed on the Scottish margin as continental slope and ocean trench sediments were wedged under the leading edge of the continent by the descending oceanic crust. On the other side of the narrowing ocean, volcanic islands were forming in what is now the Lake District and Snowdonia. Finally, by about 395 million years ago, the two continents collided, forming the Caledonian orogenic belt. The widespread folding and metamorphism was followed by the intrusion of granite masses, such as are now seen in the Cairngorms and beneath the southern uplands and northern England. The suture, that is the line along which North America and Europe finally collided, lies to the south of the accretionary prism. Such continental collisions result in intense folding and crustal thickening. So isostatic uplift occurs, leading to major erosion as the mountains rise. As the newly formed mountains of the orogenic belt are eroded, post-orogenic sediments are laid down unconformably on the folded rocks. This unconformity is on the north coast of the Isle of Arran in Scotland. Devonian Old Red Sandstone rests on late Precambrian rocks which were folded and metamorphosed by the Caledonian orogeny. This unconformity between Caledonian and younger rocks is a major feature of British geology. Here, at Sicker Point on the north coast of the southern uplands of Scotland, Old Red Sandstone rests unconformably on steeply dipping lower Paleozoic sediments. Further south, in the Pennines, we see lower Carboniferous strata resting unconformably on folded lower Paleozoic strata. In each example, we have intensely folded and even metamorphosed Caledonian rocks overlain by relatively undeformed strata. Thus we have two contrasting lithotectonic units. An older orogenic unit overlain by a relatively undeformed Devonian or Carboniferous cover unit. We can simplify the division of rock units in the British Isles into a number of such lithotectonic units. Now this model shows the appearance of these units beneath the surface of Britain. And the colour key to it is here. At the base in purple is the pre-Caledonian basement. And above it in yellow is the Caledonian orogeny. And then above that in pink is the older cover. And then finally at the top in green the younger cover. Well, in fact, we divide the rocks of Britain up into 5 lithotectonic units, but we'll come to the 5th one in a minute. Now, the boundaries between all these lithotectonic units are usually major unconformities, but there may be major faults in places. We've just been looking at examples of the regional unconformity between rocks of the Caledonian orogenic belt and what's termed the older cover. In the Cheddar area, you've seen an example of another major but younger unconformity between the Carboniferous limestone and the younger cover, which starts with the Triassic conglomerate above. Well, this map shows the surface exposures of the lithotectonic units, with basement up here, Caledonian orogeny, older cover, and younger cover. And the younger cover outcrops over most of southeast England, over the North Sea, the English Channel, and the Irish Sea. Let's remove the younger cover. The hollows in this model show where the younger cover, that's the Permian, Mesozoic and Tertiary strata, are thickest. The offshore basins here are particularly marked south of Ireland, and one of them can be traced up into Cardigan Bay. And there's one onshore, the Cheshire Basin, and a smaller one to the north beneath the Vale of Eden, which runs on into the Solway area. Look how steep its margins are. These margins and those of the other basins are faults that often moved while sediments of the younger cover were still accumulating. Now let's strip off the older cover. The hollows in this model represent the combined thickness of the younger cover plus the older cover. There are two new features here. This basin up here is the Midland Valley of Scotland. Following the closure of the Iapetus Ocean, this rift valley subsided during the Devonian and Carboniferous, accumulating sediments of the older cover. Secondly, there's this east-west trending trough in the southwest of England. This is the key to the 5th lithotectonic division. This area was the margin to an ocean to the south, the Rheic Ocean. During the Devonian and early Carboniferous, it accumulated sediments, but in the late Carboniferous, these sediments were caught up in an orogeny, folded and metamorphosed as the Rheic Ocean closed. This orogeny is known as the Variscan. This depression is a reflection both of the thickness of Devonian and Carboniferous sediments that accumulated on the margins of the Rheic Ocean and of the compression and thickening of these sediments by Variscan earth movements. Further north, the older cover was not affected by this orogeny, so we make a lithotectonic division between the relatively unaffected region, the older cover, and the deformed Devonian and Carboniferous sediments of the Variscan orogeny. Finally, let's strip away the rocks of the Caledonian orogeny. Now there are the huge depressions in North Wales, northern England, and above all in Scotland. These depressions represent tens of kilometres of rocks formed on the flanks of the Iapetus and compressed by the Caledonian earth movements, causing considerable crustal thickening. Now, of course, this model shows us the present-day surface of the basement rocks beneath Britain, and there are 3 major areas where it's close to the surface: northwest Scotland, Wales, and the Midlands. Clearly, these haven't been much affected by orogenic activity, so we can regard them as cratonic areas which, since the late Precambrian, have either been land areas or only covered by shallow seas. But of course, the Scottish area of cratonic basement and those in Wales and the Midlands used to lie on opposite sides of the Iapetus Ocean. And there's evidence that this southern basement area is much younger. On Anglesey, it contains evidence in the form of a pillow lava sequence that could indicate an early phase in the opening of Iapetus, a precursor ocean, which may have closed again in the late Precambrian. So far, we've seen evidence for how Britain has drifted northwards across climatic belts and how its rock formations can be divided up into 5 lithotectonic units. Well, let's use the exhibit now to put all this into chronological order and paint a rather impressionistic picture of Britain before man. Well, there's much dispute about pre-Caledonian history and, for that matter, early Caledonian history, but it's certain that during the Lower Paleozoic, Iapetus closed, causing the orogeny that produced the second lithotectonic unit, the Caledonian. This is a paleogeographic map for the mid-Ordovician, about 450 million years ago. The dark line indicates an ocean of indeterminate width, on either side of which you can see chains of subduction-related volcanic islands. The evidence for all this volcanic activity comes from rocks such as this. Look at this series of graded units, probably resulting from successive eruptions of ash settling through the sea. This specimen is from the Borrowdale volcanic series in the Lake District. This is a reconstruction of what North Wales might have looked like 450 million years ago. Here we find ignimbrites, such as this specimen. These resulted from violent explosive activity. They formed as an emulsion of lava particles suspended in hot volcanic gas, settled out and fused in places to produce this characteristic streaked appearance. By the mid-Silurian, the paleogeography looks something like this. Iapetus was nearly closed now, and much of the Midland Craton was covered in shallow seas, which in places were populated by crinoids and corals. The end of the Silurian brought the final phases in the closing of the Iapetus Ocean and the final phases in the metamorphism and folding of the Caledonian orogenic belt. A new lithotectonic unit, the older cover, formed from the Devonian onwards as the Caledonian mountains were uplifted and eroded. With the closing of Iapetus, Britain was united and formed part of a new Euro-American continent, often called the Old Red Continent, after the characteristic deposit, the Old Red Sandstone. This is how Britain might have looked from space 370 million years ago, at the beginning of the Devonian period. The area was still south of the equator, experiencing quite arid conditions. Sediments produced by the weathering and erosion of the Caledonian mountains were deposited where rivers ran into the vast coastal plain of the Rheic Ocean to the south and into inland lakes to the north. As time progressed, the mountains were eroded, and at the beginning of the Carboniferous, the land was invaded by the sea. This is how Britain might have looked 330 million years ago, during the early Carboniferous. Now the area was situated near the equator, and during this time, the Carboniferous limestone was deposited in warm, shallow seas in which crinoids were the dominant bottom-dwelling organisms. Most of the land between the Caledonian Mountains and St. George's Land subsided by the late Carboniferous, and much of Britain was mantled in coal swamps. At the end of the Carboniferous, the closure of the Rheic Ocean resulted in the Variscan orogeny, and rocks of this lithotectonic unit outcrop in southern Britain and southern Ireland. And by the Permian, Britain had migrated north of the equator, and as a result of the Variscan collisional event, was situated in the middle of the vast supercontinent of Pangaea. So the beginning of the Permian saw hot, arid conditions in which desert sediments accumulated as the newly uplifted Variscan mountains were eroded in the south and the older Caledonian mountains in the north. These were the first units of the younger cover, the New Red Sandstone. This reconstruction is for a period about 250 million years ago, when Britain was on the margins of an extensive inland sea. Broadly similar conditions continued into the Triassic, except that the inland sea disappeared. From Triassic times onwards, the vast supercontinent of Pangaea broke up. First, North America and Africa separated as the southern North Atlantic started to open in the early Jurassic. This division formed the continents of Laurasia and Gondwanaland. In the early Cretaceous, the South Atlantic began to open. The rest of the North Atlantic opened during the late Cretaceous and early Tertiary. Events in the breakup of Pangaea influenced the paleogeographic evolution of Britain. Arid conditions of the Permo-Triassic were replaced in the Jurassic by subtropical conditions as the area drifted northwards. And as global sea levels rose, remnants of Caledonian and Variscan mountain belts were inundated by shelf seas which teemed with life. Sea level continued to rise until the late Cretaceous, when it was probably over 300 metres higher than present-day levels. And this deep sea environment was dominated by planktonic coccoliths, whose calcareous remains form beds of chalk extending from Ireland to the Urals. The Mesozoic global rise in sea level was caused by the growth of ocean ridge systems as Pangaea broke up, the newly developed ridges displacing ocean water onto the continents. The continental breakup is reflected in other ways. For instance, the separation of Britain from Greenland and the northward movement of Africa towards Europe. Early tertiary igneous activity in the northwest of Britain, such as this columnar lava at Fingal's Cave, is coincident with the earliest phases of Atlantic opening between Britain and Greenland. Africa's collision with Europe resulted in the Alpine orogeny. And in Britain, movements of a similar age produced folding in the Younger Cover, as here on the Dorset coast. By the Pleistocene, Britain's northward drift returned it to the clutches of polar ice sheets which it had left over 600 million years ago in the southern hemisphere. It's in the deposits of one of the interglacial periods of some 250,000 years ago that are found the oldest human fossils in Britain. Since then, man's cultural development has increased exponentially. Perhaps this scene depicts one of the first geological field trips about to begin.